In this video, we're going to talk about exponential functions. So I want to do this by example, and I have here two growth scenarios for us to look at. So one is company A has 100 stores, and they're going to expand by 50 stores every year. And company B has 100 stores also, but they're going to expand by increasing the number of stores by 50% of their total each year. So let's look at how that kind of maps out. And if you don't have a calculator, grab a calculator really quick just so that you can work this out with me. And let's calculate then how many stores each company will have after 3 years. So real quick, company A is kind of easy. So they're going to add 50 stores every year. So basically right here, we add 50 and we get 150. Great. Then the next year, so we start with 150, what they had the previous year, and we add 50 again, and now we're at 200. And then the next year, using that 200, we add 50 again, and we're at 250. Great. Not too complicated. Now, store B is a little different. So store B, they're going to do 50% increase on where they're at. So right now, their 50% increase is going to be on the 100 stores. So I'm going to take 50% of 100. And 50% of 100 is 50, which is 150. Okay. So they actually have the same right there. Same number of stores right there. All right. Next year. So we start with 150, and this time we're going to take 50% of 150. And 50% of 150 is 75. So that comes out to 225 stores. Okay, so now we see our first difference. 225 stores versus 200. So they've definitely bigger amount of stores opening for company B that second year. Third year, we're going to take the 225, and I'm sure you guessed it, it's going to be even more. So now we're going to take 50% of 225. And that comes out to, sorry, I got to actually grab my calculator, 112.5. Which I guess as stores, it'd make more sense to say 113. Okay, but that's okay. I'll just pretend for a second 112.5, which comes out to 337.5, or probably just round to 338 because it doesn't make sense to have half a store. Okay, there we go. So again, they're starting to really peel away from the growth that company A is seeing. They're actually in the 300s and well into them at this point. So what we want to do is kind of understand what's going on with these two models. So for model A, this type of growth, this constant change every year, we've seen that before. That's called linear growth. But model B here is actually doing an increase as they go. That type of growth is exponential growth. Shocking, right? Since that's the title of the section. So exponential growth. It gets bigger every year. The actual growth itself gets bigger. So what we want to do is look at a couple of equations for this. So for store A, company A, that equation is not too complicated. For company A, we had that every year it's changing by 50. So that's like a rate of change, which we would call the slope. And then the starting value of 100, that would be our y-intercept, our initial value. So as an equation, it would be f of x equals, I'll use f of x instead of y, since we're going to call these exponential functions. F of x equals 50x plus 100. Cool. Okay, company B is a little bit more complicated, and I kind of like to think of it a little differently than how we did the calculations. So here's how we're going to think of it. Rather than doing this, which was taking 100 and adding 50% times 100, instead of doing that, here's how I want to actually think of this. It's actually smarter to think of it as taking 100 and multiplying it by 150%. So the 150% is taking into account the 50% increase. So they're going to have all of the original stores, that's the 100%, and plus a 50% increase. In fact, plug it into your calculator. plug that in your calculator, and what you're going to see is, I'm just going to take a second and write it down. That's going to come out to 150. Oops, there's a decimal there. It kind of floated away, but that's all right. So again, if I were to take 100 and multiply it by 150 the following year, twice now, that's going to come out to 225. And if I multiply that result again by 150, maybe I should have written it like this. Excuse me. I'm taking this right here, and I'm multiplying it by 150 again, 150%, whatever that comes out to, multiplying 150% again. So that's the increase again. Or a better way of writing that is 1.50 squared. Okay, I think that makes a little bit more sense to say it that way. And if I were to do it again, I would take then this giant number I have here, 150 times 150 times 150, and times it by another 150 on the third year, which is going to give me cubed. Okay, so that comes out to 225. I think you should pause the video, plug in your calculator, and check. This is going to come out to 337.5. And what we're seeing is kind of a pattern going on, I hope. Here, here, here. So fourth year, it's going to increase to a 4. All right, so here's the pattern we're going to use to create a little formula here. So we can create an exponential formula. There's a couple ways we're going to write that, but first, f of x. So a is like our starting amount. In this case, we'd start with 100. So a is our starting amount. Then we're going to multiply it by 100% plus whatever growth rate we're looking at. My example was 50%. So it was 1 plus 0.5. And then raised to however many years we're talking about. So that is a basic formula for growth. Another way of writing this, by the way, is I could simplify this, actually come up with a number, which is what I did. That was the 1.5, and just call it B instead. So you could actually just label it as B. And in fact, they do say that B is what's called the growth factor. So they actually have a special name for that. It's called the growth factor. By the way, it works for decay. I didn't mention that, but it does work for decay. It's just going to be a subtraction instead of an addition because we are subtracting that percentage every year. So we'll see some examples of that in a minute. Okay, so before we do that, real quick, they actually had a really cool graph in the book, and I thought it was worth taking a moment to look at. They mapped out by every 2 years for 10 years. And what you could see is the growth rate of company A versus company B is like stark by year 10, right? By year 10, A is at 1,000 here. Sorry, let me grab my red pen. 1,000 stores, where B is at 6,000 stores. Holy cow, 6 times the amount of growth in 10 years. And that's the idea with exponential growth. It just shoots off like that sharp upward climbing. And we'll talk about the graphs in the next section, but that's the difference between the exponential versus linear growth. Okay, let's look at an example. India is the second most populous country in the world, with a population in 2008 of about 1.14 billion people. The population is growing at about 1.34% each year. Let's write an exponential equation and try to use that equation to make a prediction as to what's going to happen in the year 2020. Now, we'll know what that is, by the way, because we have passed the year 2020, but that's the idea. Okay, so here we go. Let's plug in the appropriate information. So 1.14, that is going to be my A. And then the 1.34%, that is going to be R. And here I'm going to write it as 0.0134. So I'm actually change it to decimal form, right? Move the decimal twice. So according to my formula up there, did they give me any labels? They didn't. We're going to go ahead and instead of using X, we'll call it T. And I think that's because they might refer to this equation again later. So I want to use the same terminology. So f of t equals 1.14 times 1 plus 0.0134 to the t value, or another way of saying that is f of t equals 1.14 times 1.0134 to the t. Great. So there's our equation. And to predict what's going to happen in the year 2020. So in this case, our starting point was 2008. So the year 2020 would be 12 years later, right? So 2020 is t equals 12 because that's 12 years later. So we're going to find f of 12, which would be 1.14 times 1.0134 to the 12. And you are going to want to practice putting this into your calculator. Now, the exponential button on your calculator can vary. If you're using a graphing calculator, excuse me, I'm sorry, they use this symbol. It's called the caret symbol, and it's typically above the division symbol. That's the exponent button. Scientific calculators typically are using something like some form of y to the x, x to the y, a to the b, something like that, where it's actually indicating that they're doing some sort of exponent relationship. All right. Those are the most typical that you'll see. So you're going to want to enter this into your calculator until you are able to figure out how to get the number 1.337, and that would be billion. All right, so exciting. By the way, the actual answer is the actual growth in India was 1.380. So not too far off, but that's what we would get for our prediction. Okay. And of course, we know that it's not going to be perfect, right? Because we're talking about human beings here, and human beings can do some interesting things. So let's go ahead and look at these three statements and figure out which one is exponential, or which ones are exponential. The cost of a living allowance for state employees increases salaries by 3.1% each year. So that would be exponential growth. Why? Well, because if it's increasing by 1% each year, that means it's going to be growing more rapidly the longer you are staying somewhere. B, state employees can expect a $300 raise each year each year they work for the state. That would be linear growth. That wasn't really what they asked, but it's linear growth because they're adding a constant every year. And tuition costs have increased by 2.8% each year for the last 3 years. Ew, that's not as nice. The first two were nice, but not this one. That's exponential again. And really, as you can see, the key is the fact that we're increasing by 1% each year. That's that exponential growth model. Okay, now I've mentioned decay and we haven't done one yet. So let's look at an example of decay. Bismuth 210, I have no idea, by the way, if it's pronounced bismuth, we're just going to pretend it is, all right? Bismuth 210 is an isotope that radioactively decays by about 13% each day. Wow, that's rapid. Meaning 13% of the remaining bismuth 210 transforms into another atom, which is polonium 210 in this case, each day. If you begin with 100 milligrams of bismuth 210, how much remains after 1 week? Now, what we're really measuring is how much of the bismuth 210 remains after that period of time. Okay, so here we go. Here's how our formula is going to be a little bit different. So A, our initial amount was 100 milligrams. R in this case, though, is negative because we're decaying 13%. So I'll write 0.13. So in our formula then, they actually use Q for some reason on their formula. I don't know why. We'll just stick with it. And since it's by day, they use days. So instead of X, they use D, where it's representing days. So that's 100 times 1 minus now, or plus negative. Wow, that's just a weird one, and I got to fix it. Sorry. Minus 0.13 to the D. Okay, or 100 times 0.87. That's kind of cool. In other words, 87% remains after each day. There you go. That's where the 87 is. Okay, so how much remains after 1 week? 7 days. So 100 times 0.87 to the 7th. Plug that into your calculator. I'm going to actually take a second and do it. Helps when you plug it in correctly, though. And I am getting 37.7, and I'll round that to 3. 37.73, and that would be milligrams. That's how much is left after a week. Not as much, right? Not too much at all. Almost 2/3 of it is gone at this point. All right. So there's an example for decay. Let's try this example. So this one, they're actually giving us a scenario here, and they're kind of asking us to interpret what it means. So T of Q represents the total number of Android smartphone contracts in thousands held by a certain store, Verizon store, measured quarterly since January 1st, 2016. Interpret all the parts of the equation. Okay, so T of Q is by quarters, right? It's quarterly. So if we're looking at T of 2, 2 is the quarter we're looking at, and that would then imply that it's the second quarter in the year 2016. So their second quarter in the year 2016. All right. And the 86 would be representing the contracts, the starting contracts or initial contracts at the start of the year. But it's in thousands. They actually said that this thing measures in thousands. So when they write 86, that's not just 86. It's 86,000 initial contracts. At the start of 2016. Or you could just say January 1st, 2016. All right. And then in that second quarter, it looks like they ended up with 231.3056. So again, we're talking about thousands. So that would be 231,300. Here, I'll round that to 6 to make it make sense. You could put 5.6 if you wanted, but this would be the amount of Android contracts at the end of the second quarter. Probably should have capitalized Android since it's a proper name. There you go. And that's how we kind of break down that equation.